Imagine you have a collection of envelopes, each with its own unique width and height. The Russian doll envelopes problem asks you to find the maximum number of envelopes you can fit one inside the other, like Russian nesting dolls. This intriguing puzzle requires a clever combination of sorting and dynamic programming techniques to arrive at the solution. From optimizing resource allocation to managing dependencies in projects, the ability to find the longest increasing subsequence plays a vital role. The challenge lies not only in identifying the nested envelopes, but also in maximizing their count. Therefore, we must delve into the world of algorithms and data structures to tackle this problem effectively. By understanding the logic behind each step, we can gain a deeper appreciation for the elegance and efficiency of the solution. The first step in solving the Russian doll envelopes problem is to sort the envelopes in a specific order. We begin by sorting the envelopes based on their widths in ascending order. If two envelopes have the same width, we sort them in descending order of their heights. This specific sorting order sets the stage for the next step, where we apply the concept of the longest increasing subsequence. By arranging the envelopes in this specific manner, we can efficiently identify the optimal nesting order and determine the maximum number of envelopes that can fit inside one another. The sorting method described in the previous section is crucial for correctly solving the Russian doll envelopes problem. By sorting the envelopes based on width in ascending order and then by height in descending order for equal widths, we create a framework for efficiently finding the longest increasing subsequence. Consider the case where two envelopes have the same width but different heights. Sorting the heights in descending order prevents us from mistakenly including both envelopes in the increasing subsequence. By arranging the envelopes in this specific order, we transform the problem into finding the longest increasing subsequence of envelope heights. This sorting strategy is the cornerstone of the solution, setting the stage for the next step, which involves finding the longest increasing subsequence. Section 4. Finding the longest increasing subsequence. The core of the solution. With the envelopes sorted, we can now focus on finding the longest increasing subsequence, or LIS, of their heights. The LIS represents the maximum number of envelopes that can be nested within each other. We maintain an array, often called, to track the smallest tail of all increasing subsequences of a given length. For each envelope, we determine its place within this array. If the current envelope's height is greater than all tails, it extends the longest increasing subsequence by 1. This process continues for all envelopes, gradually building the array and ultimately revealing the length of the longest increasing subsequence. Section 5. Utilizing lower bound. Optimizing the subsequent search. The function plays a critical role in optimizing the search for the longest increasing subsequence. This function efficiently identifies the correct position to insert or replace an element in the array. Performs a binary search within the array to find the first element that is greater than or equal to the current envelope's height. If such an element is found, it indicates that the current envelope can potentially extend an existing increasing subsequence or form a new one with a smaller tail. This optimization is crucial because it ensures we always have the smallest tail for an increasing sequence of a particular length. The binary search nature of significantly reduces the time complexity of the algorithm. Section 6. The final output. Unveiling the maximum nested dolls. After processing all envelopes and updating the array, the final length of the array represents the solution to the Russian doll envelopes problem. This value signifies the maximum number of envelopes that can be nested inside one another, fulfilling the requirements of the original challenge. The length of directly corresponds to the length of the longest increasing subsequence, and thus, the maximum number of nested envelopes. The final output provides a concise and meaningful answer to the problem. This output is the culmination of the entire process, providing a clear and concise answer to the problem.